Welcome to this explainer. All right, let's get right into it because today we're doing something absolutely fascinating. We're taking the dense, core principles of electrostatics and electric circuits and translating them into the fundamental rulebook of the universe. By the end of our time together, we are going to map out the complete literal journey of an electrical charge. We'll track it from the moment it's just sitting there, perfectly still, all the way up to its role in powering incredibly complex engineered circuits. So if you've ever wanted a strictly structured, no-nonsense guide to how electricity actually works at its most fundamental level, you are in exactly the right place.
So let's dive right in with a pretty provocative question. What are the precise, invisible forces that dictate how charge behaves all around us? I mean, it's so easy for us to just flip a light switch and totally take the result for granted, right? But beneath that one simple action is a ridiculously strict set of physical laws. We really have to understand exactly how charged objects communicate, how they interact, and how they exert force on one another before we can even begin to wrap our heads around a modern electrical system.
To answer that, we'll be covering 4 key areas today: the fundamentals of charge, how objects become charged, variables of electric circuits, and finally, analyzing circuit systems.
Okay, Section 1, the fundamentals of charge, decoding PS.PHY.4 4.1.
The absolute bedrock starting point here is Coulomb's law. This mathematical model is what lets us understand if two charged objects are going to attract or repel each other, and it lets us calculate exactly how strong that force will be, which, surprisingly, operates a whole lot like gravity, but literally billions of times stronger. It gives us the precise math we need to understand the fundamental interactions of any charged objects in the universe.
And that logically brings us to our next non-negotiable rule, the conservation of charge. Just like energy, charge is conserved. This dictates that while electrical charge can absolutely move around, jump from one object to another or flow down a wire, the total absolute amount of charge within a closed system always remains constant. You can't just magically create new charge out of thin air, and you definitely can't destroy it. You can only relocate it. This concept is absolutely vital for balancing literally any equation or model we're going to use later on.
Moving on to Section 2. How objects become charged. Mechanisms of transfer.
So, there are precisely 3 ways we model the transfer of a charge: friction, conduction, and induction. By categorizing them this way, it allows us to systematically break down every single static electric event you've ever experienced in your entire life.
Let's break these down. First up, friction. This requires the physical rubbing of 2 different materials together, literally stripping electrons from one and depositing them right onto the other. Second, conduction. This is much more direct. It requires actual physical contact between a charged object and a neutral one, allowing the charge to just step right across that boundary. And finally, induction, which is honestly the most fascinating one. It occurs entirely without direct contact. Just bringing a highly charged object near a neutral one forces the charges inside that neutral object to completely rearrange themselves. So you have 3 distinct physical interactions, but one guaranteed result: a newly charged object.
All right, Section 3, variables of electric circuits, harnessing the flow.
Now, you literally cannot analyze a circuit without understanding these 4 core pillars. Current is the actual continuous flow of the charge itself. Actually, fun fact here, individual electrons drift surprisingly slowly, but the electrical signal itself, that moves near the speed of light. Then you have voltage, which is the underlying force or pressure that's actively pushing that charge along the path. Resistance is exactly what it sounds like. It's the environment's natural opposition to that flow, slowing things down. And finally, power represents the ultimate rate of energy transfer that happens as a result of all this movement. Understanding how these 4 variables interact is basically the skeleton key to unlocking electric circuits.
And to make sense of all this, we use circuit models. These models are our primary tools for harnessing this flow. They allow us to move way past just guessing, letting us mathematically calculate exactly how much voltage is required to push a specific current through a known resistance. So we can generate the precise power we need to, say, light up an entire city or just charge your phone.
Which brings us to Section 4, analyzing circuit systems, the architecture of flow. Notice this stark contrast in these foundational layouts. On the left, we have series circuits, which feature only a single pathway for the charge to flow. It's like a one-lane road. If that pathway is broken, the entire flow stops instantly, dead in its tracks. But over on the right, parallel circuits are characterized by multiple branching pathways. If one branch gets severed, no problem. The charge can still flow right through the alternative routes. The behavior of current, voltage, resistance, and power changes entirely depending on which of these architectures is being used. Finally, we reach the heavy hitters, compound circuits. Real-world systems rarely rely on just simple series or simple parallel lines. Instead, they combine elements of both architectures into a single, highly cohesive system. Analyzing these requires a much more rigorous, multi-step approach. You have to isolate the series components, identify the parallel branches, and rigorously apply our mathematical models just to understand exactly how the power is being transferred throughout that entire combined network. As we wrap up this explainer, I really want to leave you with this thought. We started with resting charge, right? And we built all the way up to complex branching networks. Knowing these precise mathematical rules, how do you think these exact compound circuit models scale up to power the incredibly vast continent-spanning electrical grids of our modern world? The principles are identical, the scale is just infinitely larger. Thank you so much for joining me to explore the foundational rules of our electrical universe. Keep questioning, keep analyzing, and I will see you in the next explainer.